The moon has been Earth's closest companion for nearly as long as our planet has existed, and it shaped almost everything about the world we live in. Look up on a clear night and you see a quiet silver disk. Simple, familiar. But that stillness is deceptive. The moon is not just a backdrop. It is the reason Earth has stable seasons. It pulled the first tides across ancient shores, and the story of how it got here is one of the most violent events in the history of the solar system. Let us start with the basics, because the basics are stranger than they first appear. The moon sits about 384,000 kilometers away from Earth on average. That distance shifts slightly as it travels along its elliptical path, coming as close as about 356,000 kilometers at its nearest point, and drifting out to roughly 407,000 kilometers at its farthest. Its phase cycle, the journey from new moon to full moon and back, takes just over 29 and a half days. But here's something that often surprises people. The moon actually completes one full orbit around Earth in only about 27 days. The extra 2 days exist because Earth itself is moving around the sun. The moon has to travel a little farther each month just to catch up and face us from the same angle again. Then there are the tides. Most people know the moon pulls on the oceans, but the mechanism is more interesting than a simple tug. The moon's gravity does not just pull the ocean on the side closest to it. It also creates a bulge on the opposite side of Earth, the side facing away. This happens because the near side of Earth is pulled more strongly than Earth's center, and Earth's center is pulled more strongly than the far side. The result is two tidal bulges at once, on opposite sides of the planet. And despite the sun being enormously more massive, the moon actually exerts a stronger tidal force on Earth. Because tidal force depends on the gravitational gradient, how much gravity changes over a distance, and the moon's closeness makes that gradient steeper than the sun's. Now, here is where things get deeper. That same tidal interaction is slowly pushing the moon away from us. Every year, the moon drifts about 3 to 4 centimeters farther from Earth. It sounds trivial, but over billions of years, it adds up to an enormous change, and it tells us something important. The moon used to be much closer. Early Earth would have had tides on a scale almost unimaginable today. But how did the moon get here in the first place? The answer, as best as we can reconstruct it, is catastrophe. About 4.5 billion years ago, the young solar system was still a chaotic neighborhood, full of large bodies in unstable orbits. One of them, a protoplanet roughly the size of Mars, was on a collision course with the young Earth. Scientists call it Theia. The impact was not a glancing scratch. It was a direct, oblique collision that released energy on a scale that is genuinely difficult to put into words. The outer layers of both bodies were vaporized and thrown outward into a ring of debris orbiting a battered, molten Earth. This is the giant impact hypothesis, first formally proposed in 1975 by William Hartman and Donald Davis. In the decades since, computer simulations have filled in the details. Only about 2% of Theia's original mass ended up as orbiting debris, but that was enough. Within somewhere between 1 and 100 years after impact, roughly half of that debris had coalesced into the moon. On a cosmic timescale, the moon formed almost instantly. The hypothesis explains several things that had long puzzled scientists. Why the moon has a very small iron core compared to Earth, why its composition so closely matches Earth's outer mantle, and why it formed at all, given that most rocky planets do not have large moons like this one. What came after the formation matters just as much as the formation itself. Earth rotates on a tilted axis. That tilt, currently about 23.5 degrees, is what gives us seasons. As Earth orbits the sun, that tilt means the northern hemisphere leans toward the sun for part of the year and away from it for the other part. Without any tilt, there would be no seasons. With too much tilt, the poles would receive extreme amounts of sunlight and then extreme darkness, and the climate would swing wildly. Here's the part that does not get enough attention. Earth's axial tilt is not fixed by physics alone. The other planets in the solar system, Jupiter in particular, exert gravitational nudges on Earth as they orbit the Sun. Over long timescales, those nudges could cause Earth's tilt to drift chaotically, potentially swinging from nearly upright to deeply tilted and back again over millions of years. That kind of instability would produce climate shifts severe enough to disrupt almost any form of complex life. The Moon prevents this. Its orbital angular momentum acts as a gyroscopic stabilizer, holding Earth's tilt close to 23.5 degrees against those external perturbations. Without the Moon, models suggest Earth's axial tilt could wander dramatically, pushing the planet toward climate extremes that life as we know it almost certainly could not survive. The Moon is not just a neighbor. It is a long-term climate regulator that made the conditions for life possible in the first place. This connection between a violent impact 4.5 billion years ago and the stability of every ecosystem on Earth today is the kind of thread that makes planetary science so compelling. One catastrophic event created a stabilizing influence that persisted across billions of years, and now, for the first time in more than 50 years, humans are going back. The Artemis III mission, currently planned for 2027, will land astronauts at the lunar South Pole, a region that was completely ignored during the Apollo era. The reason for the new focus is scientific, and it is substantial. The lunar South Pole sits adjacent to the South Pole Aitken Basin, the largest and oldest confirmed impact crater in the entire solar system. It is roughly 2,500 kilometers across and deep enough to have penetrated down to the Moon's mantle. The rocks exposed there are among the oldest anywhere on the Moon, some estimated at 3.85 billion years or more. Reading those rocks could give scientists a clearer picture of what the early solar system looked like, including the period called the Late Heavy Bombardment, when large impacts were still frequent throughout the inner solar system. The South Pole also contains permanently shadowed craters that have not seen sunlight in billions of years. Those craters are cold enough to trap and preserve water ice and other volatile compounds. That ice is scientifically significant because it may preserve a chemical record of early solar system materials. It is also practically significant. Water can be processed into drinking water, oxygen, and rocket fuel. The Artemis program plans to establish a permanent base camp near the South Pole, and the presence of water ice could make that base far more sustainable over the long term. The Artemis III crew will spend about 6.5 days on the surface and conduct 4 spacewalks to collect geological samples. Every sample brought back will add resolution to the picture we are building of where Earth came from, how the Moon formed, and how the solar system looked in its earliest years. The Moon has been shaping Earth for 4.5 billion years. It pulled ancient oceans into motion, steadied the planet's tilt through every era of evolution, and bore witness to every chapter of life on this world. Now, as we prepare to return to its surface, the question worth sitting with is this: what else has the Moon preserved that we have not yet thought to ask about? If you enjoyed this video, consider subscribing to the channel.